Welcome to this second video about quantum groups. It leads on from the previous video. I'll very quickly recap what we did in the previous video, but this really is a real beginner's video. It's just maybe your second day of quantum groups, and we're going to stick to finite quantum groups. We're going to talk about primarily commutative algebras of functions on quantum groups, which are basically just finite groups, and also what are called co-commutative. And we'll just at the very end introduce an example of something that's truly called truly quantum. The reason for this is a belief that you go into your text on quantum groups, and if you're an absolute beginner, there's quite a lot, maybe small details that aren't quite explained, and the hope would be that this video might do that, some of that for you. Okay. So this is from the previous video, kind of explaining what quantum space is and what a quantum group should be. So in the previous video, we argued that the algebra of functions on a finite quantum space should be multi-matrix algebra. Basically, the idea here being that this would be it's called a C-star algebra. And what are called the self-adjoint elements in here, when they look at this thing is, all these objects are bounded operators on what are called Hilbert spaces. And when you take a self-adjoint thing in here, it'll actually see a set. A set of eigenvectors. So the quantum comes from the fact that two different observables, when they look at the quantum space, can see different sets, and so they can't really be simultaneously measured, and that gets manifest as non-commutativity. That's more from we'll be moving away from that kind of language in this video. So then we were talking, okay, if that was a general quantum space or a quantum set as such, what should be a quantum group? And this is kind of the framework that we came up with. So you have here a group. Now in this video and for the rest of this is a finite group. And what you have down here are the group axioms and the group morphisms, the multiplication, the inclusion of the identity and the inverse, and the relationships between those that define this thing as a group. And what we want to look for is to translate the object, which is the group, the morphisms, the maps, and the commutative diagrams, translate them into a different category where you kind of have basically finite group but in a different setting. So we'll do a bit of that today. We spoke about it briefly last day. And this I'm calling this the quantization functor somehow, should replace this group here with the algebra of functions on it. Now, the algebra of functions on the group, this is what we'll study in detail today. And this satisfies what I'm calling, they're kind of Hopf algebra axioms, and in fact a little bit more, the C-star Hopf algebra axioms. And what you would do, what a quantum group would be, is if you have an object like this that satisfies the same axioms, has similar morphisms, but that the multiplication is not necessarily commutative. So here we say it has so these would be the translated group axioms. It has all of those, but not necessarily commutative. This is what we call the algebra of functions on a finite quantum group. Now, the two things that are actually facts here, but I would say I would like in any definition of quantum groups, is that if you have such an object that satisfies some axioms, you see, because this doesn't have to be a finite group, it could be different kind of objects here. But whatever it may be, that whenever this object is commutative, you can essentially over here and you can recover the group. That is true for what we're going to look at here, and we'll kind of outline that. And the other thing is that if you have two different commutative algebras of functions on groups, that the axioms must be such that if these two algebras of functions are isomorphic, as algebras of functions, that the underlying groups must be isomorphic as well. Now, I won't look at that. It's probably not too far away, but yeah. So this is basically the framework. So an algebra of functions on a quantum group is, well, from here it'll be a C-star algebra, a finite C-star algebra that has morphisms that satisfy axioms that look like translated group axioms. Okay, and we'll see all of these now today. So the first example we're going to look at, in fact, is these things. So actual finite groups and actual commutative algebras of functions on them. Now, the other thing we may as well do, if we're talking about these things as multi-matrix algebras, as C-star algebras, as closed subsets of bounded operators in the Hilbert space, we may as well represent these things which are very familiar to us in that language as well, in the kind of linear algebra language, and we'll do that as well. So the commutative C-star algebra of all functions, now here this is just the elements in the group, and here I've just labeled them, because if I want to represent a function as a bounded operator, the easiest way to do that is to do it with a matrix, and I have to choose a basis to do that. So I essentially choose a basis via a labeling of the group elements. So S1, so this is the number of elements in the group, that's how many things are here. So all the functions from here to the complex numbers is a commutative C-star algebra. Right. If you want to see, so I mean, whatever it may be, so however you think about function, ordered pairs, or some kind of a dynamic definition, or the function will take whatever fs, it will take s1 to f of s1, etc. If we want to view it as a bounded operator, we can just write it as a diagonal matrix. And these will all commute with each other. And that's where we're getting the commutativity. So these are all bounded operators on C, G copies of C. There are a number of elements in G copies of C. And so it lives in this thing. Now this will be a direct sum of this many one-dimensional factors. Okay. Now there's a very natural, now kind of looking now again at this picture, it has a very natural basis. These functions, it'd be the delta functions. So the delta function just is essentially equal to 1 if you give it s, otherwise it gives you 0. So that's just another way, it's another way of writing that. It'll give you out 1 if the input is the same as s, otherwise it'll give you 0. And here is how it forms a basis, because you can write every function as linear combination of the value of the function at t times delta t. And we can also put it in this language here. We can write every function as a linear combination. Now the EII is essentially the matrix with a 1 I along the diagonal. And for example then, the elements say SI would be represented by 0, 0, 0 in the ith entry of 1, and then 0, 0, 0, etc. And then the idea would be that the values of the function are the same as the eigenvalues of this. Okay, I don't think we're going to talk about this again until a little bit later. Now, what is a C-star algebra? Now, we've got topology. These things are closed. They're Banach algebras, but essentially we're in finite dimensions. They're always going to be closed. We're not really going to have to worry too much about topology. What we do have, it's an algebra in the sense that there's a multiplication, and we're going to define the multiplication on the tensor product. It's no problem, it's just a pointwise multiplication. So say f1 times f2 to be evaluated s will just be, you know, it's the same as how do you multiply the functions x squared and sine x together. Simple as that. This function x squared sine x, no problem. The involution is just the conjugate, same as the conjugate transpose here, and of course because it's a diagonal matrix, the transpose doesn't really do anything. The norm is, well, you can take the operator norm of this, which will be the same as the maximum value of the function, kind of the supremum norm. The unit is the function that's equal to 1 on all the elements, which is the same as the identity matrix here. and there's a unit map. Now the unit map might come in a little bit later when we're trying to talk about something called a co-unit, but it just sends a complex number to a complex number times this. So this is something in what's called associative algebra. The unit map basically includes something that is the unit. So the sense that it's a unit, this guy times any function is the same function. And we also have an integral, or I'm going to call it the averaging. So you can take a function and calculate its average over the group. I'm going to write this as the integral of g. Now it's a little silly really to be writing it like this, but this is kind of to look a little bit further along. But it's okay at the moment. So this thing is just averaging. So this is quite a familiar object, possibly. Nice little object. It's finite. It's just essentially a vector space, but it's got a multiplication. Now, what are we talking about here? So this thing has what's called a co-multiplication. So as it is, I mean, how does this really reference a group? It doesn't. This could just be any old set. How do we see that these things in here can be multiplied together? So this is the co-multiplication. So the way that we would have spoken about this in the last video is a way of kind of motivating how everything should work is we do this functor composition. Okay, we'll go through this nice and slowly. So this is in the category of sets, where our group is a set, and we have a morphism here. This is the group multiplication, where you take a pair of elements in the group, in the set, and you multiply them together. Okay, no problem. So this is just a group multiplication, no issue at all. Now what we do is we apply what's called the free functor. Now what this does is it takes us from a set to a vector space, but it also takes morphisms in the category of sets to morphisms in the category of vector spaces. So here what we have is that the multiplication gets turned into the multiplication in the group, gets turned into the multiplication in here. Now I may as well introduce at this stage, the object that the group is sent to is called the group algebra. And essentially what you're looking at is linear combinations of elements of the group. Now rather than writing S in the group algebra, I'm going to write delta S. And the image of this morphism under this functor essentially just says, okay, just multiply these things together. But the thing is here, you could have delta S1 plus delta S2 tensor delta T, and you could multiply them together, and you do it in a linear way. Okay, so but here you basically still see the multiplication, and then what you do is you apply the dual endofunctor. So this is from vector spaces to vector spaces, but it sends the vector space to its dual. And what it does with the morphisms is it does the transpose. So what that means is, so this here is the dual endofunctor applied to this. And so what this thing does is it says, okay, the transpose just says, if you want to do this, apply to a function, do this first, and then go and do your function. Now what that does is it has the effect of turning all the arrows around. We might see that a little bit on the next slide, and certainly in the previous video. So what this says is, okay, we've got a function here on the group. Now what that wants to take in is a single element of the group, and it gives us something here that actually takes in two elements of the group. So it's a function on the group to what looks like a function on g times g, to the ordered pairs of elements in the group. So let's see how this works. So here's the co-multiplication of f. Now we're using an isomorphism. Now I won't go into the tensor product too much here. There'll be loads of videos on this, but essentially for us, for finite groups, these things are the same. And essentially this previous line kind of it illustrates how they're the same. So it's saying that if you want to you have this associative multiplication, delta S tensor delta T is just delta ST, and that's the kind of the same as saying, okay, if you have S and T, you can multiply them together to get S and T, and that somehow these are kind of the same thing, is somehow a manifestation of this. Not exactly. So let's see how this transpose business works. So F wants to take in an element of the group, but the delta is going to allow it to take in a pair of elements represented here, not by a pair, but as a tensor product. So we're saying that this is the transpose of the nobla. Now the nobla is just essentially, it's just a linearized version of the group multiplication. But anyway, let's do it. So instead of the delta, we do the nobla of these two, which multiplies them together. And now we're going to see that essentially this delta ST and ST are kind of the same thing. We'll see this again later on, actually. It'll give us a picture for this. And all this is saying here as well, this is ST, this is, well, what did delta F do? It said, well, I had S and T, well, what I do is I multiply them together. Essentially, that's it. So we've got a function originally that takes in one element, but now it takes in two. How does that work? Well, you multiply them two of them together and then apply F. So here you kind of, this is just actually this written again. I don't know why I have this, but anyway, so it's saying, okay, here's essentially two elements in the group. The co-multiplication applied to delta S says, okay, multiply these together. Now what this implies is a formula for the co-multiplication. Now the co-multiplication, because we've applied this free functor and the dual end of functor, it's going to be a linear map. And so I can define it just on the basis elements. And remember, these are the basis elements. So this is kind of, if you think about, let's see, like, what is this to be equal to? Well, if G1 and G2 multiplied together to give me S, it gives me 1. So I need these two things to multiply together to give me 1. G1 by G2, excuse me, have to give me S, and that's how you can write that. Now this thing isn't exactly the inverse of multiplication, but it's not the worst way in the world of thinking about it, because this thing here is the same, essentially, well, looking it up here is, this is the indicator function on the inverse image of the multiplication of S. So it'll be equal to 1 in all the things that multiply to give you S. And of course, there's many of those. Now, so this is how the fact that this is a group is seen up here with this co-multiplication. And the group axiom of associativity, which can be written as a commutative diagram, under this functor composition looks like this. And this is what's called co-associativity. Now, what's going to be very important for later on is that this co-multiplication is a star homomorphism. Now, that it's a homomorphism just means that delta Fg is equal to delta F delta G, if F and G here are functions, but it's also a star homomorphism, which means that this star can be pulled out here. And in general, what you can do is you can write the delta of a function as a sum of these little tensors here. That's just like what we did here. And the involution, the star involution here, is just applied to both of them like this. So that the co-multiplication is a star homomorphism is very important in the theory. So it's worth noting here. Okay. So now all this is really giving you is the stuff about the multiplication in the group, which is essentially saying, if I'm not mistaken, just that it's a semi-group. Okay. What about the identity? Now this is kind of going into it in detail. I have no problem going into the detail. Let's see. Now there's a kind of a confusing way of that I'm going to write this down, and I kind of needed to do it properly. So this thing here is called the group algebra, this CG, and we've got a unit map here. Now what we're doing is we're taking a complex number and essentially we're including the unit in there. Now the unit in the group algebra, now the group algebra has actually been seen, it's over here, these linear combinations of elements of the group. And the multiplication in the group algebra is with this nobla. So delta S tensor delta t, multiply them together, you get delta st. If you take this to be the identity element, if S is to be the identity element, of course you're going to get the same thing. So this delta E is a unit in this associative algebra, the group algebra. So this map here takes a complex number and sends it to the complex number times that delta E. But I'm going to do a really weird kind of, there's a tensor product isomorphism here that I need to use to be completely consistent in what I'm doing, is that any kind of, well, I'm not sure exactly what object, certainly vector space, tensor with the complex numbers is itself. And so I'm using some funny isomorphisms here. So this 1 will be this delta dot. Now the dot is just to be an element of a one element set, and the unit map should send that to delta E, and this would be the same as this 1 tensor delta E. Maybe I don't, yeah, I probably wanted this to be the delta dot again. Not a big deal. So let's see. In the group, what you have is this E map. So the E map goes from this one element group just containing dot, and it includes the group element. Now we apply the free functor. Now the free functor applied to a one element set, here's that one element set, that just gives you the complex numbers. So this is just complex numbers. And the free functor applied to this morphism is this unit map. So this lambda to lambda delta E. And now you apply the dual end of functor, which says that, okay, take this function, and what you'll do is, okay, there's probably something that's missing, but we will see it later on. The dual end of functor applied to the group algebra gives you the algebra of functions on the group. We'll see that big style later on. So rather than looking at this level, we're now interested in algebra functions on the group again. And we're saying that the dual end of functor applied to this unit map is something called a co-unit. And what the dual end of functor does is say, okay, transpose me. So you've got a function here that's hopefully on the group, and you're ending up with something, well, this is where it's going to be a bit complicated, and this bit at the end is all we're going to be interested in. So let's see how it works. So we've got epsilon applied, F here is a function on the group. Here's this epsilon, okay. That is the dual of the unit map, so we're going to do a transpose, and we've got this delta, weird delta dot knocking around. So this thing says, okay, do the transpose, so apply the unit map first, and now this is where this hopefully starts to make sense. So the delta dot is sent to 1 tensor delta E, which is the same as delta dot tensor delta E. And now we're saying we're using this isomorphism here, this is essentially delta E. And this is basically the same thing as the value of the function at E. So after all this confusion with this unit map and these delta dots and the tensors, epsilon of F just says evaluated at the identity. So this is the algebra functions version of the inclusion of the unit. Now, how is the axiom reflected? The axiom is reflected like this. So this here is the group axiom of identity. You take an element of the group, you do an isomorphism where this is this dot, ordered pairs, where essentially what you want to do here is take a group element, make an ordered pair, the dot with the group element. E here is going to include the identity. So here you got E, the group identity, together with G, and this says multiply them together. So of course E and a little g multiplied together gives you G, you end up back where you started. And of course you can multiply on the left by the identity and the right by the identity, you get the same thing. Now, if you know your tiny bit of category theory, you can apply a functor to a commutative diagram, you get another commutative diagram. In this case, you apply first the free functor and then the dual end of functor, and you essentially get this but turn the other way around. So let's see this. So rather than doing multiplication last, we do the image of this morphism under the functor composition first, which is the co-multiplication first. So you do co-multiplication. Then what you do is you do the image of this, which is the epsilon, because E gets sent to the epsilon, which is the co-unit, and then you do this, and then you got this isomorphism here. So this will be the same as doing nothing. In other words, this. So this is how the group axiom of identity is reflected in the algebra of functions on the group. Now some small facts. This epsilon is a star homomorphism. Now because it's going from, I haven't it written down unfortunately, but it's going from, you take a function and it gives you a complex number, so it's a functional. And if it's a homomorphism, that means that it's a character. And what that means is, if you know some stuff about characters on certainly C-star algebras, this is going to need a one-dimensional factor in here. Now we know that already here. So for example, if you say S1 is the identity, it's kind of, you're going to see the same thing, but this is important, probably not in this talk, but perhaps in the subsequent thing. You got what's called this Haar element. Now this is a thing in 2 to the G. This just means it's a projection. It's either valued at 0 or 1. Now this thing is actually it's just equal to 1 on the identity and 0 everywhere else. And that means that the co-unit applied to it is 1, and you also get that it is central. It commutes with all other functions. Now here everything is commutative, but this is something that's going to be true for all finite quantum groups, even when the multiplication is non-commutative. And so what we see is that we can kind of decompose. This is a general thing now, not just for commutative ones. You're going to definitely have a one-dimensional factor here. And this is used in various different places. Okay. That's kind of just an aside at the moment. So essentially, this co-unit is a functional. You take a function on the group and it outputs the value of the function at the identity, which is a complex number, and you get an encoding of the group axiom of identity. Okay, so now we're up to semi-group with identity. What about inverses? So what does the inverses is something called the antipode. Now, again, we'll go through this thing again. I don't think there's any harm going through this. So the usual situation, if you look at what I call half algebras, they'll just start throwing down this. Say, oh, look at this axiom, look at this axiom. And they'll give you this axiom as well. I'm just trying to explain where these axioms are actually coming from. Okay, so here again, we're in the category of sets, and we've got a morphism, which is the inverse map, which you have an element of a group sent to its inverse. Apply this free functor, and this is what I call the free functor applied to this inverse is what I call the inverse thing, and it says delta G to delta G inverse. And then you apply the dual endofunctor here, and what you end up is with a map is called the antipode, and again it is the dual of the inverse, so it is the transpose of the inverse. In other words, the antipode says if you want to apply the antipode to S, you apply first the inverse and then you apply the function. So let's see how this works. So SF, the antipode applied to F. Now F is a function on the group. So SF in this case is going to also be a function on the group because these are going on the same level, group algebra to group algebra. S will go from algebra functions back to algebra functions. So apply the inverse inverse first. That's what doing the transpose means. The inverse just sends delta t to delta t inverse. And this is essentially the same thing as f of t inverse. And so S of f applied to t essentially just says do the inverse here. Now, there's other things. It's hard enough to write down the in the category of sets language the axiom of group inverse, but you can do it. You need these maps here. So the first is the diagonal map, which sends G to an ordered pair GG. And if you do, now here I'm just doing the functor composition as once. So you get two functions sent to their product, the pointwise multiplication. So if this diagonal map apply the functor composition, doing everything properly with the morphisms and everything. The quantum version of this, the algebra of functions version of this diagonal map, is the pointwise multiplication of the functions. The other one then here is this. This thing is called a little co-unit in G. It's a function sending essentially. I'm not sure what it's sending to, possibly the one element set, which essentially it's the one element set. So everything is sent to 1, or that dot we saw before, and apply the functor composition, and you get the unit map. There should be a little FG on this, the unit map of FG. So this is what the axiom of inverses in the group looks like. So essentially, what do you got? Take an element of the group, maybe I'll call it T here. Do the diagonal map, so you get TT. Apply the inverse to one of them, so you get T inverse T. Then multiply them together. What's T inverse by T? E, the identity. And then you apply this epsilon, which will take the identity to 1. And then this should actually be the dot. And then the E map we saw is that it'll take the, oh no, I'm doing this the wrong way, sorry. So we started with a T, and we ended up with an E. And so T here will be sent to 1, which is the same as the dot. And then the dot, or E sends the dot to E. So this is just a category of sets language for writing down the axiom of inverses in the group. And now you apply the functor composition to this commutative diagram. Of course, everything goes the other way around. So here, rather than diagonal map, inverse on one side, multiplication, we should see co-multiplication, S-tensor identity, and pointwise multiplication. And here it is. Look, going backwards, co-multiplication, antipode tensor identity, pointwise multiplication. And it's the set now. The apply the transpose to this. So the E, because you do the dual, it's a contravariant. It's going to turn these around. So E is the co-unit, and the epsilon G gets turned into the unit map. That's there. So this is, okay, we've got all this. So essentially now what we have is this co-multiplication, which goes from algebra functions to algebra functions tensor algebra functions with this relation here. We have epsilon, which the co-unit goes from the algebra functions to the complex numbers with this relation here. And the antipode, which goes from the algebra functions to the algebra functions, which satisfies this here. Together with the fact that the algebra functions is a C-star algebra, which essentially says that you can multiply the things together and it can be represented as bounded operators, which we've done back here. I think if I say that the co-multiplication is a star homomorphism, I think that is the definition of the algebra of functions on a finite quantum group. Okay. Of course, you're going to reference, and we'll see some references later on. This will all be written down carefully. Now, the S is an anti-homomorphism. This means that it gets turned around. Now, of course, in the commutative case, it's actually a homomorphism because these things will commute, but that's not true in general. Star linearity, now that is actually not true in larger categories, but in finite quantum groups it is true. So that means that S of F star is equal to S of F all starred, and it's an involution. Now, it's definitely an involution here because the inverse of, if you apply this S twice, you'll get F of T inverse, and it's simple abstract algebra to show that when you've got inverses in a group, that the inverse of an inverse is the original function. Essentially, that this thing is involution. That is not true in larger categories of quantum groups, but it is true for finite quantum groups. And it has a relation to something as well, which we might see on the next slide. Okay, let's see what's next. The next thing that's interesting, now the two things that you want to do with groups is you want to do averaging and you want to do representations. Now we're not going to quite have the time for representations in this video, but we can certainly look at the averaging. So we've got this faithful averaging functional, which now this bar here is or like undergraduate statistics, this is the average. So it takes a function on the group and it gives a complex number, and what it does is it sends the function to its average. So you got adding up the values of the function divided by the number of numbers. It's just the average, and we're going to write this as this integral of g. Right, now let's say some things. I'm missing one thing that I wanted to say. I'd say this thing is it's faithful. What that means is the only time it gives you 0 on a positive thing. Now a positive function is of the form f star f. Now this is the conjugate. So essentially all this means here, its values are positive real numbers, possibly 0. And that it's faithful means that when you take the average of a positive function, the only time it gives you 0 is when the function itself is 0. So that's what the faithfulness means. Tracial, which I haven't got written down here, means that if you take the average of function 1 by function 2, you get the same as the average. I think I was trying to write it here, but I'm missing the other integral, so that you can change the order here. Now, of course, in this, we're still talking about the commutative algebra functions. This is true, definitely. But in a larger category, this isn't always true. And in fact, pretty much this is true whenever this is true. But in the finite, in the commutative case, they're both true. And in fact, in the finite quantum groups, they're both true. So this is a faithful trace, this averaging function. It's also what's called a positive linear functional, because if you give it a positive thing, which is a function which only takes on positive real values, it'll spit out positive real values. In other words, if you take a function that takes values that are all positive real numbers, take the average, it's not going to be complex, it's not going to be negative, it's going to be a positive real number. The other thing is that if you give it the unit, this is the function that's equal to 1 on everything. Well, the average of that is you're just adding up loads of 1s and dividing by the number of 1s, you'll get 1. This, because in cahoots with it being what's called a positive functional, this thing is called a state. So it's faithful, positive, tracial, state. And for finite groups, these are essentially the same as the probabilities. And we might see this in later slides. So this thing, it's called the Haar State. And the other thing it has is, and it's a kind of a property of groups, that they kind of all look the same in certain senses. If you draw what's called a Cayley graph, it kind of looks all the same. And what it means is, if you're averaging a function and you translate it, which means that, say, instead of looking at the average of f, but you look at the average of so take a function that's value, its value at s. Now look at its value at ts, and average over the s and over the ts, you get the same thing. This is called invariance, and it's very, very powerful, particularly in something called representation theory. And the Haar State has this invariance. Now, if you want to translate this thing here, this invariance, which is true in a much larger category, it gets turned into something like this. Okay, so this is invariance, faithful, tracial, state. Okay, this is the Haar State. What are we going to look at next? Duality. So one of the slides the recall slide, one of the things that's very important is that if this thing is commutative, you can recover a group. Now, the second thing I won't worry about too much. So we'll just roughly describe, if you've got an algebra of functions that's commutative, how do you recover the actual group? And this is the duality. So this Q goes in one direction. Duality says it must also come back. And this is essentially what's called Gelfand duality. So this is a commutative C-star algebra, and there's a big, okay, and now we've got some objects called characters. So the characters are the homomorphisms from the functions to the complex numbers. We've seen one of them, which was the co-unit. That was such a homomorphism. And there's a big Gelfand theorem for C-star algebras using more machinery than we see here that says that the essentially when you've got a commutative C-star algebra, it is isomorphic. Well, if it's unital, now this one is unital because we have this thing. If it's non-unital, we have to do some messing around. It's isomorphic to the continuous complex valued functions on the characters. Now, because we're in finite dimensions here, essentially, whatever way we want to talk about continuous, everything is going to be continuous. So it's the functions on the characters. Now, it turns out that the characters on the algebra functions are just these delta t's. Now, what these delta t's are, they also might be called, I'm not sure what they might be called, t hats maybe. So the delta t applied to a function says, now remember, it must take a function to a complex number. It says, here's a function, delta t applied to it is the value of the function at t. And there is one character for every element of the group. So essentially what we have is the characters on the group are in a kind of bijective correspondence with the elements of the group. So that's where you're getting your set. Now, where do you get your multiplication from? Another theorem in C-star algebra says that when you've got a star homomorphism from Cy to Cx as continuous functions on y, continuous functions on x for us, finite y and x are just, it'll be all the functions. There exists a continuous function going backwards from x to y. Now, it's a continuous function from x to y such that this star homomorphism is in fact the transpose of this. And remember, the transpose, I'm missing a little sub-pi. We've seen this thing before. So the co-multiplication is a star homomorphism, so there exists a function going in the other direction from essentially, and again these could be f's, from g times g back to g. That goes from g times g back to g. And so there is such a function that can easily associate for us an ordered pair g1, g2 with another element of the group. And you can use co-associativity of delta to show that this multiplication is associative. And I assume that there's similar tricks with the co-unit, which is a star homomorphism. And I'm not sure exactly what happens with the antipode, but the fact that it's an anti-homomorphism is surely going to be important. And I think that's going to give you something like G1, G2 inverse is you turn around the G1 and the G2 and you get G2 inverse, G1 inverse. Okay, very good. So this is how you recover from the algebra of functions, the group. Now there'll be a little tidying up to show that if you get different such objects here, that you get different objects here. And that would be enough to cover what I'm calling fact 2. That would make these this quite good. Now we've got another duality going on as well. And there's other dualities, I don't know how to pronounce it, so I won't try it, but there's another famous duality, but this is duality on one level. There's another one here. So we've got the free functor to the group algebra and the dual endofunctor to the algebra functions, but that dual endofunctor is pretty much an involution. So either by stopping here or more interestingly, going from here back, which is the way I'm going to think about it, this is going to be another algebra of functions on a finite quantum group, which we're going to call the dual group. Okay, now the dual endofunctor, basically what we can do is all the morphisms here, the pointwise multiplication, the co-multiplication, the antipode, the co-unit, the unit map, and maybe, I think that's pretty much everything. We can apply the dual end functor to those and get stuff in here. So for example, the dual end functor of the pointwise multiplication gives us a co-multiplication here. The dual end functor of the co-multiplication here gives us the multiplication here. And because the dual end functor is a functor, contragradient, the commutative diagrams here get transformed into commutative diagrams here, and so we can take the algebra structure here, apply the dual end functor, and we're going to get what's called half algebra axioms here. In other words, we're going to see this, we're going to see this, we're going to see this. And what that means is that the group algebra has a structure of algebra functions on a quantum group, which we call the dual group. Now, there's different things about when G is abelian and stuff, but we won't worry about that today. Now, this is going to be the picture for this, because occasionally what we're going to have, okay, so we're going to think of this as the algebra of functions, and this we're going to think of as the group, but also we're going to think about it as the group algebra, because essentially what we're saying here is that the elements of the group, okay, so the traditional way that you would look at functions is you got an element of the space and you apply the function to the element in the space and you get a complex number. And that's, that's the way we think of things. But there's a duality which says that instead of thinking of the function being applied to the element and producing the complex number, you can think of the element being applied to the function and producing the complex number. So you can write f of aj, but you can also write aj of f. This is this is called a double duality, and it's essentially a way of saying that if you do the double dual, it should be the same thing. Now for us, this kind of duality is essentially, we've kind of seen it a little bit. So this would be a function on the group, and this you can think of as, say, an element to the group S, or delta S. So f of S is like f of delta S. And the other thing is you can think of, now you wouldn't put the S here, but the delta S applied to the function, which I think we had back here, is the same. The delta S applied to the function says evaluate me at S. And this is kind of an observable state duality. So both the algebra of functions and the states as such, both can be considered algebra functions and spaces. So essentially this is just an excuse for me on the next slide, I think, where I'll have, instead of f of say S, it'll be like delta S of f, and that these are actually the same thing. Right, let's talk about this dual group. So we're going to do it this way. We're going to take the algebra functions, which we've described in great detail over these pages, and we're going to apply the dual end functor to it. Now the dual end functor sends a vector space to its dual and sends a morphism to the transpose of the morphism. So this is saying that, okay, the dual end functor applied to the algebra functions gives us, now we're cheating a little bit, we'll probably be fixed in the next page. There we're okay, but this essentially is all the linear functionals from the algebra functions to the complex numbers. And these can all be written as linear combinations of these delta t's. So essentially what we're seeing now is, if you know your smallest bit of dual vector spaces, so the delta t's on the bottom are a basis of the algebra functions, and the delta t's up top are the dual basis. Okay, now we can get a multiplication in this thing. Now I could keep calling it the group algebra, this is what it is, but we're going to call it the algebra functions on the dual group. So we're going to get an algebra, a multiplication on the algebra functions on the dual group. So these things are functions on the dual group, which means they're functions actually from, well, they're functionals from the algebra. So what they should do is take a function on the group and give you a complex number. So let's see, how do they do that? So you can use the dual ender functor applied to the co-multiplication in the algebra of functions to give you a multiplication for the group algebra. Now this does happen to be the same as the so we've got a multiplication here, apply the free functor, you get a multiplication in the group algebra, or the way I'm doing it here, almost to be awkward, is I can take the co-multiplication, apply the dual ender functor, and that's another way to get multiplication here. So let's see it. Okay, this says do the transpose, so that means first apply the co-multiplication here, and we know how to do the co-multiplication, we've seen it previously. It'll be delta st inverse tensor delta t, and then you apply this tensor product of these functionals and you get something like this. This is also what's called the convolution of these functionals. We might see that later on. Okay, so that's a way of multiplying things in the algebra functions on the dual group. We can also get a co-multiplication on the algebra functions on the dual group by applying the dual ender functor to the pointwise multiplication in the algebra functions on the group. So this thing must, what this is supposed to do, the co-multiplication, we must start with a function on the quantum group, and it must give us a tensor product of functions on the quantum group. So here we start with a function on the finite quantum group. And of course we need to, how have we not said this yet? The multiplication here is non-commutative. For example, if this is delta s up high, delta g up high, and multiply them together in this sense, you get delta sg, which mightn't necessarily be the same as delta gs if s and g do not commute in the group. So anyway, so this thing should give us originally something that is in here, but eventually is a tensor product of these, which should be able to deal with a tensor product of functions in here. So let's see how it works. It says, okay, the co-multiplication, the dual co-multiplication should be apply the dual to the pointwise multiplication, which means do the transpose. So do the multiplication in here, do that. That means multiply the f1 and f2 together. So we're going to get the delta s applied to f1, f2, and then we use this little duality to say that that's the same as f1 delta s, f2 delta s. Pointwise multiplication. So you go back, this would be the same as just throwing in delta s tensor delta s. So you get this kind of trivial kind of an object, but this is the co-multiplication in the algebra functions on the dual group. It is okay to be a little bit confused here, but this is doing this properly. Similar story. The next one is not too complicated. So the antipode on this thing is the dual of the antipode. So apply the antipode first, which essentially will amount to doing f of t inverse. So the antipode looks kind of the same here. The co-unit here is a bit simpler in that what it does is, okay, let's see. The antipode in this algebra functions on the finite quantum group, that is the dual group, is the dual of the unit map. So apply the unit map to 1. So the unit map applied to 1, the unit map of the algebra functions is this indicator function on the whole group. And this will always give you 1. Because this is saying evaluate this at little g, but of course this always gives you 1. This is 1. And this amounts to, slowing it down, the co-unit on any of these elements is 1. These are all linear maps, so defining them on these are the basis elements is fine. And these 3 maps will satisfy this axiom, this axiom, this axiom, and this thing is also a C-star algebra. The representation in terms of matrices is a little bit more complicated, but it can be done usually using representations. What about the star situation? Well, these things, delta S star is delta S inverse. The indicator function on the dual group is now the delta E. So if you take anything in here, and you multiply it by delta E. See, the multiplication here is not pointwise multiplication, but is this kind of essentially comes from the multiplication of the group. You're going to get the same thing, and the Haar state on all these is going to be equal to 1, and this will be suitably, it's faithful. Averaging, no. It is a state. It is tracial. What am I missing? Well, it's positive as well. Most importantly, it's invariant. So that's an algebra of functions on a finite quantum group. That is not commutative if G itself is non-abelian. But it's still connected with a group, isn't it? So we're getting nothing really weird here. And in fact, you can show that every... the thing about this thing here is if you swap these around, how does this work now? If you swap these around, you end up with the same thing. And all quantum groups that are like that, where you apply the co-multiplication and then swap them around, it's the same thing as just applying co-multiplication. That's what's called co-commutative. And my understanding is that all co-commutative algebras of functions on finite quantum groups are of this form. So there's nothing new here. So are we going to see something that is new? No, not yet. Maybe on the next slide. Apologies. Now there's a nice duality that really shows, that this dual group and the algebra functions on the group are kind of how they're related. There's I wouldn't say bijection, but a correspondence. Now they're not isomorphic things. I mean, the algebra of functions is commutative. This isn't in general. But there's a nice little Fourier duality, which we can see. So one thing is you can turn a function into a functional, with this little Fourier transform, where essentially, how do you turn it into a functional? Well, take a different function and integrate, and multiply and integrate. So this goes from, this is a function, this is a complex number, and this is how you turn a function here into a functional. So that's a nice little thing. You can, because the Haar state is faithful, define an inner product on this. Well, I suppose we could have done it way back in our diagonal matrix representation, but we do it here. And because of finiteness, I've got a little bit of cheating here. So this should probably be like VG dashed to say it's the dual, or maybe VG star, whatever. But the image of all of these things, so all the functionals you get like this, is the same as all of these. So essentially what that means is all elements of the algebra functions on the how do we say this, on the dual group, come from Fourier transform of things in the algebra function on the group. So what I'm saying here is that for all functions on the dual group, there is a function on the group itself which kind of implements it by multiplying and integrating. So all these things have densities. So essentially you've got this correspondence between functions on, it's just there's a correspondence between these two. Sure, it's right there. It's the finiteness and the Riesz representation theorem, which means that there's this is invertible. So function, Fourier transform, functional, density. And that allows you to go between the two. And everything works really, 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 really nicely here for finite quantum groups. This can be done in general. You get convolution theorems, Plancherel theorems, and a lovely interaction with representation theory, which has been very important in my own research. So the interesting thing is here is that in all these slides, we've spoken about actual groups, but a lot of this holds more generally for objects over here. So what holds over here? What still survives? Well, nothing here. We have a co-multiplication. This survives. That has this property. That survives. it's a star homomorphism that survives. The co-unit, which is a functional, that survives. It satisfies this. That survives. There is a special Haar element that survives. There must be a one-dimensional factor. The antipode, going from the algebra functions on the quantum group to the algebra functions on the quantum group, survives. This axiom survives, that it's an anti-homomorphism survives. Star linearity in this survives for finite quantum groups. Finite quantum groups also have faithful, positive, invariant, tracial states that survives. The duality won't survive in this sense because you won't be able to recover a set anymore. But this duality still survives. You can take a finite quantum group and talk about its dual. That survives. And the multiplication can be given as the dual of the co-multiplication. The co-multiplication can be given as the dual of the multiplication. That survives. We get lots of things surviving. The Fourier duality survives. So let's look at one of these. Now I won't look at it in detail because particularly I won't look at the co-multiplication because it's a bit messy. So the smallest quantum group that is not commutative, so it's not the algebra functions on a finite group, it's not co-commutative, so that it's not the dual of a algebra functions on a finite group, is the finite quantum group of Katz-Paul-Eucken. Now it's 8-dimensional. Perhaps in the previous video, should it be considered of order 6 or 8? I'm not sure. It is got 4 of these and 1 of these. So that shows it's, how do we say, non-commutative. And you'd have to look at the co-multiplication itself to show that it's not co-commutative. I'm not going to write down the expression for the co-multiplication. If you want to see it, go into this paper, Franz and Gom, Random Walks in Finite Quantum Groups, to see what's going on. But basically what you get is, so I call this A1, the one-dimensional, and the two-dimensional. It turns out that if you take any of these, say E2 for example, the co-multiplication of E2 would be tensor product of stuff in here plus tensor product of matrix stuff. And conversely, take something in here, for example, E11, and the co-multiplication of that would be something from here, tensor something in here, plus, and linear combinations of something in here plus tensor something in here. That's just a little tiny flavor of it. The Haar state, the faithful, positive, tracial, invariant state, looks like this. Now the 8 is the normalizing. It's essentially kind of a trace thing here, and it's twice the this is a 2x2 matrix, twice the trace of this. If you want to read about what this is saying, it's in Franz and Gom. The dual of this object is isomorphic as a algebra functions on a finite quantum group. I don't know too much about that. And then one thing that's interesting that might pop up in a later video is this thing has quasi subgroups. Now we can talk, and we will be able to talk about subgroups of finite quantum groups. So these will be somehow sub-objects that are in their own right algebras of functions on quantum groups. And in particular, they will be closed under the involution. There are objects in here that look very much like subgroups. So in a certain sense, it's going to look like when you multiply two of them together, you get another element in there. Not quite now, but there's a certain sense we can say that. We have idempotent states. So if you average, well, I can't quite go into that here, but basically got these objects that look like subgroups, but they're not, because they're not closed under involutions. The E21, the conjugate transpose of this, you get E12, it falls out. So you get an issue. So this is something very, very different to algebras of functions on finite groups. This was discovered in the 90s, probably should have been discovered before that. Unfortunately, you could already see it in this one. But anyway, just some small facts. This was first introduced in 1967. I recommend trying to get your hand on this paper. It's fantastic. It's translated from Russian. Just a brilliant, brilliant paper. Highly recommended. But this is your first one. So the co-multiplication here, okay, it satisfies all the co-associativity. The co-unit is just the coefficient of this factor. So that the E1 here would be the Haar element that was referenced back here, a projection. What else have we got? The star is just the normal adjoint, the conjugate transpose. The antipode is actually the transpose. And I've given the Haar State, so that's pretty much everything about it. The other famous examples are something called the cyclinic quantum groups, where you get, I think, n squared of these and then an mnc. And the other ways that you can kind of make things is do tensor products. For example, if you take a commutative and a co-commutative, do a tensor product as long as the co-commutative one, let me think, is non-abelian, you'll get something that's neither commutative nor co-commutative as well. So hopefully that's given you, so really what we focused on actually was the algebra functions on finite group, its dual. I kind of spoken a bit more about the axioms, and now we're going to say that there's more such objects out there. Now for further reading, there's some archive things. So this is, sorry, self-promotion, apologies. It's my thesis. Section 2 will write all this stuff in detail. Section 1 of this talks about finite groups. Section 2 of this talks again, quantum groups. And the next is the same as the first video. Finite is too restrictive. Straight away, when you look at quantum symmetry groups of finite sets, you get compact quantum groups. So loads of material here on that. If you want to learn more about that, very good here. Chapter 2. That's probably talks some similar stuff to we spoke about earlier on. I like this, and you got everything you need here. So hopefully that was enlightening. Thank you.